Our final speaker before we go into our panel discussion, I'll remind you again to please put any questions into the Q&A, is Dr. Evan Davies, who'll be giving us a global perspective on energy systems. Evan Davies, pronouns he, him, is a professor in civil and environmental engineering, where he teaches environmental hydrology, systems modeling, and fluid mechanics courses. His research focuses on water resources planning and management, and particularly on the simulation of large-scale water and energy systems. He enjoys hiking, camping, skiing, reading, and time with his family. Thanks so much, Evan, and we'll let you share your presentation.
All right, so I'll talk to you now about global systems, energy, and everything else. You've already seen a little bit about the complexity that can exist within energy systems. And so you've seen that they can exist at many different scales, with sizes from residential all the way up to sectoral or regional. I'll talk about global scale systems and time that ranges from seconds or minutes all the way up to decades, where we're talking about infrastructure and changes in society. In terms of complexity, our analysis can focus on single energy types, as you've seen, or it can focus on some of the larger socioeconomic and environmental factors, or some of the loops or feedback effects of decisions. And so the question that I'll try to answer here is, what about the big picture of energy systems? Here we'll look at large-scale systems that are provincial all the way up to global in scale, and long-term, looking at the present day through to about 2100. And of course, we'll look at complex systems that comprise systems of systems that have lots and lots of feedbacks. And so to give you an idea of the sort of systems we're talking about, here's this figure on the right-hand side that shows energy systems, water, land, ecosystems, human health, transportation, and urban systems all linked together. And then we have all of these different factors within these systems and drivers of change. So then we have these big complex systems. How can we actually understand them? Well, of course, governments, businesses, and the public want to know the effects of their actions and their plans, both in the near term and in the longer term. And they have a couple of different ways of trying to figure out these effects. Of course, this is difficult with complex systems. And so some options are just to guess the answers, use a sort of gut feel. You can test your ideas on a limited scale. For example, try one thing, see what happens. You can ask the public, you can have surveys, figure out what they prefer. You can ask experts, and they'll tell you which sorts of policies are available and what their possible implications are. And then finally, we can use computer models. Now, some of you may ask, what is a computer simulation model? Well, here's a definition I like. This is from science fiction, from Isaac Asimov. And he wrote back in 1988, if you want to understand some aspect of the universe, it helps if you simplify it and include only those properties and characteristics that are essential for understanding. If you want to determine how an object drops, you don't concern yourself with whether it's new or old, is red or green, or has an odor or not. You eliminate those things and thus do not needlessly overcomplicate matters. The simplification you call a model or a simulation, and you present it either as an actual representation on a computer screen or as a mathematical relationship. Such simplified simulations make it far easier to grasp a phenomenon than it would be if we had to study the phenomenon itself. And to show you how complicated some of these models are, here's an animation of a global climate model from NASA. I won't show you the whole thing, but I'll give you an idea of what it actually looks like. Okay, and so here's 2015 through 2028. And you can see temperature patterns shifting across the planet. Okay, so this again is all from a simulation model, a global climate model. Okay, here's an alternative simulation. So these are not predictions, these are scenarios where we can see the potential implications of different decisions. Okay, so there's some output from a simulation model. And I'll go to the next slide. Okay, an alternative is what's called an integrated assessment model. These two are models of global systems. IAMs are computer models that simulate alternative futures under climate and other large-scale changes. So these models include many different global sectors. They include energy, land use, agriculture, buildings, transportation, water, climate, and emissions. And you can see there are lots of interconnections between these systems if you look at the image on the right-hand side. So we have at the left-hand side of that image, fine-scale Earth systems through large-scale Earth systems. These are the natural systems. Then we have physical systems that are affected by humanity. And then finally, we have socioeconomic systems. And so these will be things like the economics that drive some of the changes in physical systems and vice versa. So you can see there are feedbacks between all of these types of systems. Now you may ask, what can we use them for? Well, IAMs can be used to answer questions like, how might emerging technologies like photovoltaic cells or new batteries influence how energy is consumed and used? What might these changes mean for greenhouse gas emissions, air pollution, international markets for fossil fuels, and access to energy? How might changes in population, income, or technology cost alter things like crop production, energy demand, or water withdrawals? And how do changes in one region's demand for energy affect energy, water, and land in other regions? And of course, what are the effects of these changes now and potentially 100 years from now? I'll give you an example so that you can get a little bit of a grip on some of these ideas. So I'll talk about a research project that my group at the U of A is involved in. And we'll talk about here the global change analysis model. So GCAN is a well-known open source community integrated assessment model that's developed by the Joint Global Change Research Institute, or JGCRI, in College Park, Maryland. The U of A, JGCRI, and Environment and Climate Change Canada are working together to develop a 13-region, 10-province, 3-territory version of GCAN Canada for future energy scenario analysis. Our aims are to, 1, prepare GCAN Canada to support decision-making for new energy and environmental policies, identify promising national, provincial, and corporate strategies and compare different outcomes. 2, apply GCAN Canada to questions related to oil sands development, renewable energy options, and industrial development. And 3, in the longer term, apply GCAN Canada to questions related to land use, agriculture, and water resources, again at that 13-region scale, so that we can differentiate, for example, policies in British Columbia from Alberta, or Quebec from Ontario, or wherever. A little bit more information on GCAN. GCAN simulates energy, land, water, socioeconomic, and climate systems. It has 32 different regions that include Canada, the USA, China, Europe, and India, and 27 others. You can see them all here on the left-hand side. In terms of energy, it models fossil fuels, so resource production, through electric power plants and renewables. That's the energy transformation component. And then it also simulates end uses in the building, transportation, and industrial sectors. And you can see a little bit more about how that component of the model works in the bottom left-hand side of this image. It also simulates the growth of food, feed, and livestock, a bunch of different crop types that are used for feeding people as well as feeding animals. It simulates also water, so both the supply or the hydrology at a river basin scale, and you can see all of the different river basins that are represented over here on the left-hand side again, as well as the demands for agriculture, for industry and energy production, and for domestic purposes within households. It also simulates climate and emissions, so the releases of greenhouse gases and corresponding changes in temperature into the future under different scenarios of releases. It simulates economics. And so GCAN solves for market prices in energy, agriculture, and water sectors that balance the supplies of energy sources, for example, with the demands for all of these different markets. And it runs at 5-year time steps from the current time, 2015-ish, 2020, to 2100. So it is a very complicated model, of course. In terms of sample applications, I'll talk to you about a project that we recently did for hydropower production. This was conducted by a master's student and some colleagues from GCRI. The master's student is Evan Arbuckle, and I think he's on the meeting right now. In terms of context, hydropower produces 60% of Canadian electricity, and the capacity is expanding. However, at the same time, we have a problem, which is that several large hydropower projects under development have seen significant cost overruns. So you may have heard of Muskrat Falls in Newfoundland and Labrador, Kiask in Manitoba, and Site C in British Columbia. These are not unique to Canada. This is actually a very common problem. Such cost overruns are actually common in many places in the world. And so what we did was we made some changes to modeling hydropower in GCAN. We made it part of the overall energy system. Historically in GCAN, hydropower has been modeled as what's called a fixed output. That means that we assign a certain amount of energy production from hydropower over the time period from 2015 through to 2100, and that just happens in the model. It doesn't respond to markets. So hydroelectric generation used to be preset for each scenario. We could have higher levels or smaller levels, but it wasn't responsive to markets. There would be no expansion of hydropower if hydropower was cheap relative to coal, for example. Further, hydropower did not actually affect a region's modeled electricity price. The electricity price came from thermal power, so coal, natural gas, also from some renewable sources. Okay, so we made some pretty significant changes. And so our aim for this study was to explore hydropower capacity expansions and cost overruns. And our research questions were, how does capturing the cost of hydropower capacity expansion affect its share of Canada's electricity generation over time? So if, for example, we're looking at net zero energy in Canada, or zero emissions into the future by 2050, for example, maybe some of our electricity should actually come from hydropower, which is emissions free. So then we were looking at an exploration of changes in the electricity system that were caused by endogenous hydro, so that hydropower capacity could expand given some signals from policy, from government. Secondly, how does endogenous modeling of hydropower affect electrification of end-use sectors? So the demand for electricity in industry, in buildings, in transportation, electric vehicles, and so on. And here we were looking at the ripple effects of changing electricity prices through the energy system and onto electricity users. And third, how does inclusion of historically observed cost overruns for Canadian hydropower plants affect electricity production and end-use sectors? And so if you model hydropower as unreasonably cheap, for example, that will have implications for future expansion in hydropower as simulated in this model, right? And so here we were looking at the effects of greater realism in hydropower costs on Canadian energy systems. This is a little screenshot of the paper in case you're interested in seeing more about this. Okay, and I should mention that these are our views, not the views of the Government of Canada. Okay, so here are some results, at least briefly. Our first question was, what happens if we have endogenous hydro? And what we found was endogenous hydro becomes a larger part of the electricity mix. So here we have the historical simulation running from 2010 through 2050. You can see that hydro is important. It's about 60% of the total mix, and it reaches 417 terawatt hours for Canada. If we model hydropower endogenously, though, And so its expansion is determined by model forces, by economic forces, rather than by preset trends. It reaches a reasonably significantly larger number here. So we're up to almost 500 terawatt hours from 417. And you can see it sort of crowds out some of the other energy sources, electricity sources. Our second question was, what happens if we include cost overruns? And it does what you would expect. So if we include cost overruns, they do reduce hydropower capacity increases. And so here is the sort of experimental approach we took in this table on the left-hand side. We simulated effects of various levels of cost overruns, from sort of moderate increases in costs all the way up to extreme increases in costs, 100% more expensive. And we looked at the effects of various different technologies. So what if we only had the cost overruns for hydropower? And what happens if we include cost overruns for other technologies that often experience cost overruns as well, like nuclear power plants, or some of these newer ones like carbon capture and storage, or integrated gasification combined cycle, which is a coal-fired technology. Okay, and here's what we found. So here's the endogenous hydro as the first image here. And you can see how we're explaining the range of cost overruns and which technologies are affected in green and blue, respectively. Okay, and so you can see in terms of results, cost overruns decreased hydropower. Okay, and so you can see that comparing 495 versus 464 versus 404 versus 376. And you can see that as we incorporated more technologies in these cost overruns, we crowded out, or rather, hydro became relatively more preferable as other technologies also experienced cost overruns. Okay, the other interesting thing that happened was cost overruns also decreased electricity generation. So hydro became more expensive, that drove up electricity costs. And so rather than electrify in industry and transportation and households and buildings, instead people just continued to burn natural gas in their furnaces at home, or they burned coal in industrial processes, and so on. Okay, so we got the sorts of results we expected, but it's nice to be able to see the future trajectories under these different scenarios. In conclusion, then, you can see that energy systems interact with a huge number of other systems. And so you've seen a couple of examples now of hydropower. We have science and engineering. We have the electricity system, so infrastructure as well. We have economics playing a role, and we have society. The other thing I hope I've shown you is that we have tools to analyze even these really complex systems. So we can explore alternative energy futures with computer models. Models like GCAN help us to weigh our options, and we can see local and global effects of available energy, water, land use, and climate policy choices now and all the way out to 2100. Okay, thanks for your attention.